All right, so now what we're going to do is alkyne reactions. Alkynes are triple bonds. We got a lot of these. Some of these are similar to alkene reactions, and some are pretty different. So let's go through each one of these here. Okay, HBr, 1 EQ, 1 equivalent, 1 mole. We're saying just it's going to react with 1 pi bond only. So HBr, it is still a Markovnikov reaction with triple bonds. So for each one of these, I'm not going to go through the entire mechanism, but I'm going to talk a little bit about the intermediate, about some things to consider, Markovnikov, because that's how you put this stuff together. It's not just purely memorizing the product. That's not going to serve you well in this class. So HBr1EQ, again, 1 pi bond is gone. So now that you have a double bond, you can go back to zigzagging, right? Because alkynes have to be linear, but double bonds and single bonds don't. So now we're going to get rid of 1 pi bond, go to a double bond. We're going to keep that isopropyl group over there on the left-hand side. And then the bromine adds to the more substituted side. Really important here is that you might think, wait a minute, if there's a carbocation here, wouldn't it shift over to that position because that's more stable? The difference is with alkyne reactions, there is no shift of the carbocation, and that's really only with alkynes. Of course, alkenes, the double bond starting material, those we could see carbocations shift. But for something about the mechanism here, and there's a lot of theoretical reasons why, we just don't see carbocations shift with alkynes. Okay, what about if I had a second equivalent? So I'm just doing the same thing, but now twice. Well, now both pi bonds are gone. So we're going to react with both pi bonds, keep the isopropyl over here, and now you'll add 2 bromines to the more substituted side. So that's just a review, essentially. That's just a nice quick overview of those reactions. What if we had Cl2 1 equivalent or Br2 1 equivalent? If you go back to thinking about the alkene reactions, the double bond reactions, this is a very similar intermediate, a similar mechanism. This is going to be our bridged intermediate. So we make the bridge, right? Then we attack the bridge and we have an anti-attack. So again, it's 1 equivalent, right? So we still have a double bond because only 1 pi bond reacted. We still have that isopropyl group over there on the left-hand side. The point of that's really just to kind of give it some stereochemistry, right? So to give it something that makes it not symmetric, or something that gives it some visual confusingness to throw you off on the exam. But the idea is the chlorines are anti. Remember, we can't show wedges and dashes on an sp2 hybridized carbon because it's flat. It's totally in the plane. So what we do is we show 1 chlorine pointing down and 1 chlorine pointing up. So we show that up and down anti-addition, and we show the E-alkene. So you might see sometimes that this favors the E-alkene. Yeah, because it's an anti-addition. One is up and one is down. If I added Cl2 again, well, then we'd add another chlorine to either side. Sometimes to throw you off, though, you might see it like this, where it's Cl2 1 equivalent, which gives us this, and then Br2 1 equivalent. You're like, well, that looks a little bit weird. What's the point of that? If I had Cl2 2 equivalents, let me just show you what would happen here. If I reacted what we just had up above with another equivalent of Cl2, well, now you lose the other pi bond. So you'll add on another chlorine here, and you'll add another chlorine here. So you'll add 2 chlorines to either side. But because there's no chiral centers, we lose the ability to show that they are anti to each other. So it's like, yeah, I mean, these are anti, but you can't tell because there's no chiral centers. So one of the ways that they do that to try to kind of trip you up or just make it more confusing is Cl2 once and then Br2. The difference is there, after the Cl2, we're going to get the same product as above. So I'll show you here, we got the Cl's on opposite faces, and we still have the double bond. That is after Cl2 1 equivalent. So that's just kind of step 1. That's the 1 Cl2 reacting. The difference is now when you add in the Br2 1 equivalent, well, you're going to have the same result. Chlorines have to be anti and bromines have to be anti. But now because you have chlorine and bromine, now we have chiral centers. So we'll have a chlorine here. Maybe this chlorine is on a wedge. The chlorine here, where this chlorine is on a dash. And then the bromines add, and those are anti to each other. The bromine here would be on a dash, and the bromine at the top would be on a wedge. Now, that might look strange having the dash and the wedge on like the end of a chain. Well, if it helps, remember there's also a hydrogen here. That's what makes that carbon a chiral center. So this is one option. The other option would be the enantiomer of this as well. But this is a way that they can kind of trick you to show you like it is still anti, whereas if it was just Cl2 twice, you don't really have the ability to show all of that. Okay, let's keep moving on. What about NaNH2 with CH3CH2I? And again, I'm giving you kind of an example of this because NaNH2, remember that reaction, all we're doing is taking the H off the end of it. So like after step 1, you're going to get a very reactive, very sticky carbon. The way I like to think about it, of course, we have the H ripped off. Now that carbon is a very good nucleophile. It's very reactive. It can go attack some things. CH3CH2I. It could be just CH3I. It could be CH3Br. But the point of that is I've got a 2-carbon chain with an iodine. That is an alkyl halide. And remember, primary alkyl halides are really good at doing SN2 reactions because they can get attacked very easily if you have a strong nucleophile. And sure enough, we do. We've got our carbon with a negative charge. So this attacks, we kick out the iodine, and this extends the carbon chain. So we can use this to extend. This is what we call our alkylation reaction, where we extend carbon chains longer. So when you're drawing this, by the way, it's nice to draw the triple bond first because that is like your reference. So draw your triple bond first. On the left, we'll have that isopropyl group. Okay, that's still there. On the right, now you're adding in 1, 2 carbons to the right-hand side. So we're adding in 1, 2, and we can start zigzagging again once you get past that triple bond. So you're adding in 1, 2 carbons. That is your extension of the carbon chain reaction. Remember, it only works if the triple bond is on the end of the chain. It does not work with double bonds or single bonds like this. Only alkynes, only triple bonds can do this. Next 2 reactions. I'll put these kind of together because they are very, very similar, and we should try to compare them when we're thinking about the mechanisms and thinking about the intermediates. So our first one is mercury. So think, mercury is Mark, whereas the second one is boron. Boron is anti-Mark, and that was similar to what we did with double bonds as well. Double bonds, we had a mercury reaction that was Markovnikov. We had a boron reaction that was anti-Markovnikov. So for the same sort of intermediates and the same sort of mechanisms, we get a very similar result. So with mercury, what we get is, the way to visualize this is, first, we lose 1 pi bond. So we have a double bond here, still have the isopropyl. And then, same thing down here, I'm going to put these together. I'm doing this in steps because this is probably the best way to think about this is you lose a pi bond. With mercury, you put an OH on the more substituted side. With boron, you put the OH on the less substituted side. But in both cases, this is not the final product. So don't just stop the video now and be like, oh, Peter told me this is the right thing. This is not the final product. Remember, this is what we call the enol intermediate. So an enol is, it's like an alkene mixed with an alcohol, so we call it an enol. It is not the final product, but it helps to visualize and compare the 2 of these because they both put an OH. Mercury is just on the more substituted side, and then boron is on the less substituted side. Then they both go through that kind of very quick, very easy, very product-favored reaction we call tautomerism, where essentially, and again, I'm not going through the full mechanism here, but we're swapping the position of this H and the double bond or the pi bond. So you basically turn the carbon to oxygen single bond into a carbon to oxygen double bond, and this H goes on to the end of the chain where the other pi bond was. So you end up, in this case, with a ketone, and then the enol here does the same sort of process where you put the double bond between the carbon and the oxygen. So now you have a carbon-oxygen double bond on the end of the chain. Don't forget your isopropyl here. And then that's it. But typically on an aldehyde like this, we draw the H coming off the chain as well. And you can rotate that if you want. Like if you want to draw this as maybe a more standard looking aldehyde with like your carbon double bond oxygen pointing up in the air, sure, that's the same exact thing. These 2 are the same thing. So don't draw them both, but I'll just make a note. Or pick one or the other. It doesn't matter, honestly. Some people like this because it's more standard and we're maybe used to seeing that more. But the point is, mercury, when there's a difference in substitution, like 1 carbon has carbons coming off and 1 carbon just has an H coming off, mercury ends up with a ketone and the boron reaction ends up with an aldehyde. So that is your final product, remember, not your enol. But sometimes drawing enol is helpful. And even if the question doesn't specifically ask for the enol, it might be good to visualize it that way regardless. One note about this. R2BH. That is one of the ways of writing these reagents. Other ways would be like SiA2BH, really anything with a bunch of carbons and then some boron attached to it. So like if you see a boron and you see just some big carbon chain on it, that is the similar reaction where you have a big bulky group attached to boron, and that's to prevent some of the double additions that we might have. But it does end up with your anti-Mark OH addition, whereas mercury is Mark. So remember, mercury, think Merc is Mark. Boron is anti-Mark. Okay, those are your two hydration reactions of alkynes. Let's do the 3 reduction reactions of alkynes together. So our first one is H2 palladium. H2 palladium or H2 platinum or H2 nickel. These, remember, this reacts with any pi bond that it sees. So it doesn't stop at the double bond. It goes all the way to the single bonds. So what this would do here is I've got a 1, 2, 3, 4, 5 carbon chain. 1, 2, 3, 4, 5 carbon chain. It gets rid of all of my pi bonds. That's it. It just goes all the way to the alkane. It can't stop at the alkene because if you stopped at the alkene, well, you've got more H2 and palladium in the system. It's just going to keep reacting and go all the way to the alkane. So that doesn't allow us to stop. It's not picky, it's not selective. It just goes all the way to the alkane. On the other hand, H2 Lindlar or dissolving metal reduction, these allow us to stop at the alkane. So Lindlar's catalyst, if you ever see this written out, it's palladium with calcium carbonate, and we have some things like quinoline with it as well. So the point of this is usually to avoid writing all of that stuff, we just write Lindlar's catalyst. What this is, it's a slightly less reactive metal catalyst. So it'll allow you to react with the first pi bond, get down to the double bond, okay, and then stop. So unlike H2 just palladium, we call it poisoned palladium, which is a little dramatic, but the point is it gets down to the double bond and it stops. So the difference is Lindlar's catalyst produces a cis alkene, whereas Na with NH3 liquid, this produces a trans alkene, if there is a difference, and there's going to be a difference in these two. So Lindlar's catalyst, I will get the cis alkene. Sometimes, again, just like a little tip for drawing, I would draw the cis alkene first, and then draw everything else attached off of it. So like here, 1, 2, 3, 4 carbons. This is 1, 2, 3, 4 carbons. So on the left there, I've got 2 carbons coming off. So there is my isopropyl group. On the right, nothing. That is my cis alkene. What about Na with NH3? I said this gives you the trans alkene. So here, drawing a trans alkene is a little bit easier because that's just our normal zigzag for the double bond. So I've got my double bond here in the middle. There's my trans alkene. On the left, this is where the isopropyl group is. So that's H2 Lindlar versus dissolving metal reduction. And that is the rest of our alkyne reactions that we have here. So we're going to go ahead and move on.